time. It feels like an obvious thing. 1 second passes, then another. By the time I finish this sentence, it's been like 9 seconds into the video. You and I assume we're living inside the same now. Like you don't even think about it. But you see, Einstein asked an almost childlike question. What would a flash of light look like if you could chase it?
And remember the principle of relativity. Being at rest and moving at constant speed must be physically indistinguishable.
And what happens to time if two people are moving differently, but both trust their clocks? And once you take this into account, the idea of a single universal time is simply falling apart.
If it were possible to travel faster than the speed of light, then all of the comprehensibility breaks down, and there are a lot of awkward things that can happen, such as effects preceding causes.
And finally, questions about whether time itself is continuous or broken into pieces.
What we experience as smooth, continuous time could be an emergent effect. Time may feel continuous even if, at the smallest scale, it is fundamentally discrete.
So let's delve into today's topic. Okay, so Einstein, where do we start?
Okay, fang damit an, dir etwas Einfaches vorzustellen, Harry.
Wait, English please. I don't speak German.
Sorry. I'm saying that you can start by imagining something simple. An astronaut flies past you at a very high speed, let's say about 80% of the speed of light, and he's carrying a clock.
Alright, so I'm standing still, and he's moving fast, and he's got a clock. What am I supposed to notice? Okay, let's just pause here for a second. Before we answer that, let's be precise about what we even mean by a clock. Now let's continue.
Let's build the simplest possible clock. Take two mirrors. Let a beam of light bounce between them. And since light travels at 300,000 kilometers per second, or about 1 billion feet per second, that translates to 1 foot in a nanosecond, a billionth of a second.
So if the mirrors are separated by 3 feet apart, the light clock will tick every 3 nanoseconds, right? Okay, I'm with you.
Now let's give the same clock to an astronaut flying past you at 80% the speed of light. Now here, the astronaut is at rest relative to his clock. But from your point of view, the mirrors are moving sideways while the light is bouncing between them. So instead of going straight up and down, the light traces out a zigzag path. When the light leaves the bottom mirror, the top mirror has already moved to the right. When the light comes back down, the bottom mirror has moved even further to the right. So the light travels a longer path than 3 feet. Now, Harry, here's the key question. Does the light speed up to keep the timing the same?
No, I don't think so. Because one of our starting assumptions is that the speed of light is the same for everyone. I mean, if the light travels farther, the speed of light stays the same. Then something else has to change.
Right. You measure the diagonal path and find it's 5 feet long. At 1 foot per nanosecond, that's 5 nanoseconds per tick. Now if 15 nanoseconds pass on your clock, you would see 5 ticks on your clock, but only 3 ticks on the astronaut's clock. But we have a problem here.
Yeah, I can see it. From his perspective, nothing strange is happening. His clock looks normal.
And remember the principle of relativity. Being at rest and moving at constant speed must be physically indistinguishable.
So if only the light clock slows down, the astronaut could compare it with his clock and say, I must be moving.
And that's not allowed. So every clock on the astronaut has to slow down together. Otherwise, motion becomes detectable, and that would break Newtonian relativity.
So the key idea is that there's no absolute clock running in the background of the universe. Each observer carries their own version of time and space.
Cybersecurity.
The speed of light always stays the same, no matter who's moving and no matter how fast. And once you accept that, everything else follows. Time dilation, length contraction, and eventually the realization that now isn't something the universe agrees on at all.
I watch you fly by, and the faster you go, the slower time ticks for you. There's an actual property of the fabric of space and time under those conditions. Your clock still ticks as far, you still got your heartbeat, all of this.
We did a lot of digging while writing this video, and one of the things we looked into was the original Einstein paper from 1905. Let me open that real quick with my PDF reader right here. Like here, when Einstein derives that tau is this, he states that the time marked by the clock is slow by this factor, which is why we say nothing special is happening to the astronaut in the earlier part. Because according to Einstein, a clock at rest in its own frame ticks normally. And then the transformation between t and tau is essentially what we refer to when we say light takes a longer diagonal path. So we can annotate that directly here on the PDF. By the way, I'm using UPDF to do all this, and they're the sponsor of today's video. They have some really solid features that let you read and annotate any PDF. What if time behaves differently at the microscopic level than the time we experience in everyday life? What if time itself is discrete for particles, but feels continuous to us? Once again, I had a conversation with the Roblox Einstein, but this time I didn't cut his response short. I also tweaked his creativity parameter to the max to see what kind of answer we'd get. So here it is.
If electrons truly jump instead of moving smoothly, maybe the jump is in time. At the quantum level, time may not flow continuously the way we experience it. Time could advance only when interactions happen, event by event. Between those events, the electron is not moving through time in the classical sense. What we experience as smooth, continuous time could be an emergent effect created by countless microscopic events stacking together. Just as motion looks smooth even though matter is atomic, time may feel continuous even if, at the smallest scale, it is fundamentally discrete. So the electron's sudden behavior may be hinting not at strange particles, but at the limits of our idea of time itself.
What do you think about these ideas? I think many of you might disagree, and that's fine. We're leaving this open, at least until someone finally figures it out. But who knows, maybe that someone is you.